Hi, we will discuss now the potential of carbon nanoparticles as embedded sensors for structural health monitoring in wind turbine blades. Structural health monitoring of wind turbine blades can be realized by different ways. Among them, piezo or microelectromechanical systems, optic fiber, strain gauge or fiber optic cables, laser ultrasonic imaging. A few decades ago, carbon nanoparticles were obtained. First, fullerenes, next, carbon nanotubes, more recently, graphene, and Mxenes. The nanoparticles are much stiffer and stronger than glass or carbon fibers, and can be conductive. That led many researchers to the idea to use the materials to implement additional functionalities in composites. Nanoparticles can build conductive networks, layers or fibers, creating the conductivity path in the material. The electrical resistance of the materials with nanoparticles is changed under deformation and failure, due to changing, eventually broken, contact between adjacent carbon nanoparticles. The tunneling resistance between two adjacent nanoparticles also changed, due to changed distance between them. This led to the idea to design sensing network in composites, similar to the nervous system of humans. There have been dozens of European, American and other projects, seeking to develop such embedded sensing system for aerospace and other applications. But how to develop such nervous system for wind turbine blades? Human nervous system developed over millions of years. A number of technologies of embedding the conductive particles into composites have been developed. Among them, mixing nanoparticles into polymer, fuzzy fibers, with nanoparticles growing on fibers, sprayed coatings, electrospun nanofibers, and other solutions. Mixing nanoparticles is carried out using the high shear mixing process. However, the nanoparticle increase viscosity of the resins. Further, carbon nanoparticles tend to agglomerate, creating potential defect sites, instead of conductive networks. This problem can be solved by functionalization of the particles. Another quite promising technology is so-called fuzzy fibers. The fibers in composites are covered by a layer of aligned carbon nanotubes. This can be done by thermal-chemical vapor deposition, or electrophoretic deposition. As a result, the region with high content of nanoparticles is formed around fibers in the composites, which improves their interface properties, and also make them conductive. A quite efficient and easy scalable technology is spray coating. Nanoparticles are introduced in the fiber preform, rather than in the resin. And one more technology to mention is electrospun fibers with nanoparticles. There are advantages and disadvantages of different conductive nanoparticles. Graphene sheets ensure better interlocking with polymers, and also larger crack deviation, leading to enhanced toughness. An interesting solution is hybrid reinforcement, with graphene and carbon nanotubes. Such hybrid nano-reinforcements tend to create good networking structures, and reduces aggregation. Recently, new type of 2D nanoparticles were developed, called Mxenes. Mxenes are atomistic thin layers of transition metal carbides, nitrides, or carbonitrides. Mxenes combine metallic conductivity of transition metal carbides and hydrophilic nature. Due to high variability and lesser tendency to aggregation, Mxenes are very promising materials for embedded sensing application. Graphene and nanotube reinforcement in polymers and composites enhance their toughness and fatigue resistance. Up to 15 times higher fatigue lifetime was observed. Thanks to graphene reinforcement, we observed 40 to 70% higher shear strength of carbon composites, with carbon nanotubes in fiber sizing. A number of computational models of nanoparticle reinforced polymers and composites have been developed. There is a working assumption that unique properties of nanoparticles, as differed from microscale particles, are related with their interface properties. Namely, the nanoparticles create a layer of disturbed polymers around them, with constrained polymer chains, and changed properties. This effect can be taken into account in the computational models by using so-called effective interface model. For the analysis of conductivity and sensing performance, the percolation models of distributed nanoparticles, taking into account also tunneling effect, are used. Here, you can see an example how a structural health monitoring system can be designed on the basis of nano-engineered composites. But how far are we with this application in praxis? In fact, not too far. A group at Case Western University in the United States manufactured a blade from polymers, reinforced by carbon nanotubes. A group at Fraunhofer developed anti-icing coatings, based on carbon nanotubes. Nano-engineered wind turbine blades are still at the medium technical readiness level, and tested mainly in laboratories. What are the main challenges for the development of blades with embedded sensing system? Apart from the technology, it is environmental aspects of carbon nanoparticles. Possibility of recycling of carbon particle engineered polymers. Development of reliable control system for embedded conductive network. Let us summarize the observations. The idea to use conductive nanoparticles to create embedded nervous system in structural composites is quite attractive and promising. However, the step from laboratory tests and proof of concept to industrial application is still in future. Here, you can see the list of our publications in this area. Feel free to drop me a line, if you need some of them. Thank you for your attention.